In this video, we'll be looking at rational functions and determining the limit at infinity by observing the end behavior of the graph. Some guidelines to follow when you're finding limits at infinity for rational functions. If the degree of the numerator is less than the degree of the denominator, the limit is 0. In other words, the line y equals 0 is the horizontal asymptote of the graph. If the degree of the numerator is equal to the degree of the denominator, the limit is equal to the ratio of the lead coefficients. So the line y equals a over b is the horizontal asymptote of this graph of this function. Notice the lead coefficients are a over b. And if the degree of the numerator is greater than the degree of the denominator, the limit does not exist. Let's look at an example. Find the limit of each by examining the end behavior of the graph. Our first limit that we're going to find is the limit as x approaches infinity of 3x squared minus 6x minus 24 over 5x squared minus 26x plus 3. Now we can use our guidelines and see that the degree of the numerator is 2, the degree of the denominator is 2. Since the degree of the numerator and the degree of the denominator are equal, the limit is going to be the ratio of the lead coefficients. So the limit is going to equal 3 over 5. Now let's look at this from a graphical point of view. If you're talking about infinity, these terms to the back of the 3x squared and to the back of 5x squared are really not going to make a difference on the behavior of the graph. When you square a number that's really, really big, subtracting smaller numbers is not going to affect it that much. So this graph behaves like y equals 3x squared over 5x squared. Now we can simplify this ratio by canceling the x squareds off, and so the graph itself behaves like y equals 3 over 5 at the ends of the graph. So when x is approaching a positive infinity or a negative infinity. So this equation represents the horizontal asymptote of the graph of this function. That's why the limit as x approaches infinity will be that number. Let's do another example. If we use our guidelines, we can see that the degree of the numerator is 2, the degree of the denominator is 1. Since the degree of the numerator is greater than the degree of the denominator, the limit of this expression does not exist. And again, if we just examine these first terms and simplify that, x squared over x simplifies to just x. And as x approaches infinity, then that ratio is going to approach infinity. So the limit does not exist. Look at one last example. The degree of the numerator is 1. the degree of the denominator is 2. Since the degree of the denominator is more than the degree of the numerator, the limit of this expression as x approaches infinity is equal to 0. Again, if we think about it at infinity, just looking at those lead terms, this behaves like 2 over x. And we know that the graph of 1 over x looks like this. And so at infinity, the line y equals 0 is our horizontal asymptote. So basically what we're looking at is the asymptotes, the horizontal or oblique asymptote. This one would be an oblique asymptote. So y equals 0 is our horizontal asymptote for this type of equation. So the limit is 0.